So we want to look at one more 2D example that relates to force of gravity. And on first inspection, it might look like the exact same question we just did, but we've slightly modified it to make it, well, significantly more challenging. So this time, we still have three 50-kilogram masses, but we want to find the net gravitational force acting on sphere 1. So this time, we're finding the net force on this guy here. So the FBD, let's draw it. So the free body diagram, we are going to have a couple forces. So first of all, mass 3 is going to attract mass 1 towards it because we're always going to draw it from the perspective of mass 1. So we're going to have this F13. What's going to make this more complicated this time is you have to remember that the force acts along the line that joins the centers of the objects. So between 1 and 2, the line that joins their centers is that line there. That means that force between 1 and 2 is going to act along that line. So we're going to have this F12. This force is not in the x direction, nor is it in the y direction. The problem we're going to have is that's going to make things a lot more complicated. This is going to require some resolution of forces and all of that fun stuff. So for this, I'm going to call east and south to be positive, because I only have forces going in the east and south direction anyways. So we want to find the net force acting on this object. First of all, we need to find the magnitudes of these forces. Now, F13 only acting in the x direction or the east direction, that's easy enough. So we're going to find the magnitudes of these forces first. So we're going to determine the magnitudes of F12 and F13. So let's start with F13. So the magnitude of the force of gravity between 1 and 3, we have g times mass 1 times mass 3 divided by that distance between them squared. So we're going to have that 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Both masses are 50 kilos. And again, centimeters, we want that in meters. So we get that 0.050 meters. So 0.05 meters squared. And then what is this going to give us? Oh yeah, it's going to be the same as last time. So it's going to be 6.67 times 10 to the minus 5 newtons. So that force there, it is acting in the positive x direction. We'll leave the sign alone, no problem with that. F12, this one's going to be challenging because A, it's acting along an angle, and we also have to find that distance here. Well, that distance along here, this R12 is just going to be this squared plus this squared square rooted, because this also forms a right triangle. So we're going to have that 0.050 meters squared plus that 0.05 meters squared. So we do that, we'll get about 0.0707 meters. So that is the distance along this line here. Now let's calculate that magnitude. So I have F12, it's going to be g mass 1 mass 2 divided by that distance R12 squared. So the only thing we're changing is that R value. Up top, g is still the same. The two masses are still 50 kilos. And now let's see here. This time we got that 0.0707 meters squared. Divided by that squared. So we'll get about 3.335 times 10 to the minus 5 newtons. Now we have to start laying a little bit of foundational work on this, because keep in mind we need to break this up into components. So we're going to need to break this up into x and y components, because the vector that we actually have here is this vector here along this line. So that's my F12. And what I'm going to want is I'm going to want an X component for that. And I'm also going to want a Y component for that. Because again, when we do the final wrap-up, we want the total X component and we want the total Y component. Now we also need an angle in here. Now we have to kind of go back a little bit here. If I go back to my diagram, the angle I'm looking for here is going to be this angle in here. Now again, you'll notice these two sides are exactly the same. What that tells us is that this angle here is 45 degrees. So that force 1, 2, it's acting at an angle of 45 degrees south of east. Now the reason that this question probably chose 45 degrees is just so that if you mix up sine and cosine anywhere, you won't get the wrong answer, because cos of 45 is equal to sine of 45. But anyways, let's break this up into components. So for my X component, it's going to be this F12, and then I'm going to require cosine, because F12 is going to be my adjacent side. So we're just going to take that force that we calculated and we're going to multiply it by cos of that angle. Times cos 45. And then we are going to get about 2.358 times 10 to the minus 5 newtons. Now, this component of the force is going to the right or east, and we've called east positive. We will leave the sign B on that. We'll keep it as a positive. And then F12y, same idea. We're going to take the magnitude of that force along this line here. We're going to multiply it by sine of the angle, since F12y is just going to be sine. Sorry, this is my opposite, so we're going to need sine. So we got 3.335 times 10 to the minus 5 newtons times sine of 45 degrees, which is going to give me 2.358 times 10 to the minus 5 newtons. So with that said, I've now broken this up into an X and Y component. We've called south positive. This component's going south. We're going to leave that as a positive. So we want to find the total components in each direction. So we're going to find total X. We're going to find the total X and Y components. So F of X, it's just going to be that force of 1, 3. So we're going to have the this piece, because it's only going the X direction, plus the X contribution of this. So we're going to have this F12X. We've already dealt with sines, so we're just going to add the two pieces together. So we get this 6.67 times 10 to the minus 5 newtons plus this 2.358 times 10 to the minus 5 newtons. So this is going to give us our total force in the X direction. Oh, let's see here. Calculator's doing a funny thing. Alright, let's try that again. So we're going to get about 9.028 times 10 to the minus 5 newtons. So that is my contribution in the X direction. For the Y direction, F13 is only in the X direction, so there is no contribution to the Y direction. The only thing contributing in the Y direction is the Y component of this force. So this piece here, which we've calculated. So we know that Fy is just going to be the Y component of F12, which we've already found to be this 2.358 times 10 to the minus 5 newtons. At this point, we've done the hardest parts. We have our total X component of the force. We have our total Y component of the force. So now we're going to determine our resultant. So to find our resultant, we have our two components here. So we have this Fx component. So I got this piece here. I have my Y piece down here. And then of course my net force is going to be along this line here. So to find that net, and then the X and Y components are going to make right angles. So we have to find two parts. We got to find the magnitude and then the angle. So the magnitude we know is just going to be Pythagorean. So we got fx squared plus fy squared. So we have our two pieces here. So we get that 9.028 times 10 to the minus 5 newtons squared plus this 2.358 times 10 to the minus 5 newtons squared. So we're going to square root all that. And we're going to get our component, we're going to get a magnitude. And let's see here. So we're going to get about 9.3 times 10 to the minus 5 newtons. So what that does is that gives me the value for the magnitude of the net force. So the net force acting on sphere 1 is going to be 9.3 times 10 to the minus 5 newtons. Last thing, we want to find the angle, like how far south of east is this acting. So to find the angle, I'm going to use the inverse tangent of Fy over Fx. So these are not the same, so we can't say it's 45 degrees. So Fy is going to be that 2.358 times 10 to the minus 5 newtons. And we're going to divide that by this 9.028 times 10 to the minus 5 newtons. So I'm really crammed for space here. I don't have a lot of room to put stuff, so we're going to make the best of the situation. So if we're really careful with the calculations, we're going to find that this angle, it's about 15 degrees. And then based on what I've drawn here, I've drawn 15 degrees south of east. So to wrap this question up, I'm going to say that the net force acting on sphere 1, it's 9.3 times 10 to the minus 5 newtons, and it's acting 15 degrees south of east. Or if you'd like to say it's acting 75 degrees east of south, that's also perfectly fine. So this is a significantly more challenging problem because our two forces are not at 90 degrees to one another. So we have to resolve everything into components and add them up, then determine the resultant. But this isn't any different than things we've already done already. It's just an extension of things that we've done previously.